Let's take a look at the LightGBM, the 12th topic of machine learning. In the first part, we will look at the histogram-based split finding. To understand LightGBM, you need to understand XGBoost first. Since this video only covers what has been added to XGBoost, I recommend that you watch the XGBoost videos first. This video was produced in Korean and translated into English, and my voice was generated through AI, text-to-speech. Let's take a look at the full table of contents. In Chapter 1, we will look at the histogram-based algorithm. Let's take a quick overview and explore the histogram-based split-finding algorithm through a simple example. Then let's look at the parallel processing method and simply implement it with code. Chapter 2 examines the GOSS algorithm called gradient-based one-side sampling. And in Chapter 3, we will look at the EFB algorithm called exclusive feature bundling. In Chapter 4, we will briefly look at the depth-wise and leaf-wise methods in which trees are created. And finally, in Chapter 5, we use the LightGBM library to analyze the Santander Bank's customer satisfaction dataset. The LightGBM was proposed by Microsoft's Guolin Key and others in 2017 to process the large amounts of data more efficiently than XGBoost. Gradient-based one-side sampling, exclusive feature bundling, EFB, etc. were proposed to process the large amounts of data. The paper on the left is that Guolin K and others proposed the LightGBM in 2017. The paper on the right provides a good explanation of the histogram-based split-finding algorithm. In this video, we will mainly look at the contents of this paper. Let's look at this algorithm through a simple example. Data feature X and the target Y are like this. And the data ID are from 0 to 19, with a total of 20 data points. The target Y is for binary classification data consisting of 0 and 1. As we did in XGBoost, we set the initial prediction to 0.5 and compute the negative residual, G. And the Hessian, H, is calculated as follows. The initial prediction and H are 0.5 and 0.25 respectively, and are the same for all data points. Now let's create a frequency distribution table for this data. The number of bins is set to 5. We then divide the feature X values into 5 sections as follows. And we assign the data to each section. The value of data ID number 3 is 0.06, so it falls in the first bin. And the value of data ID number 17 is 0.22, so it falls in the second bin. We then sum up all G values of the data points in each bin. The results are as follows. Next, create a histogram using the frequency distribution table. The sum of G in the first bin is 2.5. And the sigma G of the second and third bins is 0.5. The last bin's sigma G is negative 1.0. This histogram can be created with the Python code on the right. The weights parameter is set to G. In this histogram, we can set 4 split point candidates like this. We want to find the most optimal split point among these 4 candidates. There are 4 candidate points like this. First, divide the node into left and right using the first candidate. Then we calculate the sigma G values of the left and right nodes as follows. The sigma G on the left is 2.5, and the sigma g on the right is the sum of all these values. We then calculate the left and right scores using this formula used in XGBoost. Please refer to the XGBoost videos for this formula. Then add up the scores on the left and right sides. This is the score after splitting the parent node. If you subtract the score of the parent node before splitting from here, this becomes the gain. The candidate with the biggest gain is the best split point. The score before splitting is common to all, so the third candidate becomes the best split point. We can see that it is optimal to split the parent node into left and right nodes using the third candidate. If we divide the above data into left and right based on the best split point of 0.6, it is as follows. This is the result of splitting the node using the histogram-based split finding. Next, let's look at the algorithm of histogram-based split finding. In XGBoost, we looked at the exact greedy algorithm, the approximate algorithm, and the weighted quantile sketch algorithm. The exact greedy algorithm is accurate, but takes a long time. XGBoost proposed these two methods to shorten the time. Here, we use the histogram-based algorithm to reduce the time to find the best split point. Let's look at the data on the right. There are two features, x0 and x1, and the target y is either 0 or 1. This is the root node. We want to split this node into left and right nodes using histogram. First, we create a histogram for the feature x0. The number of bins is set to 10. The y-axis is the sum of g. G is the negative residual of the data point. If the initial prediction is 0.5, the blue data point's g is negative 0.5. The sum of the g of the data points in this bin is this much. In this way, we calculate the sum of g over all bins. Since there are 10 bins for each feature, we only need to split the root node 9 times for each feature. There are a total of 9 candidates in this histogram. We use these candidates to split the root node and find the best split point with the highest gain. If this point is optimal, the root node can be split into the left and right nodes as follows. This time we create a histogram for feature x1. Set the number of bins to 10, the same as for feature 0. The sum of the g of the data points in this bin is this much. There are 9 candidates in this case as well. We use these candidates to split the root node and find the best split point among them with the largest gain. If this point is the best, the root node will be split into the left and right nodes like this. Among A and B, the one with the greater gain is selected as the final best split point. Next, let's look at the algorithm 1 presented in the paper. The capital I stands for training data, and D stands for the depth of the tree. M is the feature dimension. Initialize node set and row set like this. 0 means the root node. The first element of the row set is a list of indices of the data points in the root node. Split the root node to depth D. Next, nodes are read one by one from the node set list. Initially, the node set contains only the root node. Next, the features are read one by one. In the figure on the right, when k is 0, it is the first feature, and when k is 1, it is the second feature. And then read the indices of the data points in the node from the row set list. It's the indices of entire data points at first. Use this data to create a histogram. We read these data points one by one and assign them to each bin. Here Y stands for G, and N stands for H. In the case of regression using mean squared error, as seen in the XGBoost video, H is 1. For classification with binary cross-entropy, H is the value calculated by this formula. This algorithm uses 1 for H, assuming that the mean squared error is used. Then, find the best split point for each feature, as shown in the picture on the right. That's the process up to here. After scanning all the nodes and all the features, we update the row set and node set lists. Split the root node into the left and right with the best split point we found. The split node numbers are 1 and 2, and the node set list is updated to 0, 1, and 2. 1 means the left node, and 2 means the right node. And the row set list contains the indices of data points in the root node, the indices in the left node, and the indices in the right node. This process is repeated until the tree reaches a depth of D, i.e. max depth, resulting in a tree like this. This is the histogram-based algorithm 1 presented in the 2017 LightGBM paper. Now let's look at the parallel processing. Histogram-based algorithm takes a long time to generate a histogram each time a node is split. But the time can be reduced through the parallel processing. It is advantageous when processing the large amounts of data. Let's take a look at the contents of Fang Chengfu's 2019 paper. We have Fth feature of all instances. There are a total of n data points, numbered 1 through n. F is the feature number. Then Q bins are created. Q denotes the number of bins. As we saw on the previous page, each bin becomes a candidate for a split point. And then assign each data to its corresponding bin. Here, G is the negative residual for the data point. This is the first-order gradient that we looked at in XGBoost. The first data point belongs to the second bin, and the second data point belongs to the first bin. Then we sum up all G values in each bin. And we do the same for the second-order gradient H. When using mean squared error, H is 1, and when using binary cross-entropy, H is the value calculated by this formula. Then with the sigma G and sigma H of each bin, we calculate the gain using this formula. This formula is also what we looked at in XGBoost. Find the split point with the highest gain among all candidates. In this picture, this is the best split point. This is shown in figure 3 in the paper above. Now let's look at the parallel processing. The figure on the left is for just one feature. This time, we will look at the data with two features. Cut this data in half and use two worker threads to create histograms for the top and bottom data points, respectively. The worker thread 1 creates the local histograms of G and H for features 1 and 2 for the top data points. And the worker thread 2 generates the local histograms of features 1 and 2 for the bottom data points, just like the worker thread 1 does. The histograms created by each thread are combined to create the aggregated histograms like this. We then use these histograms to find the final best split point, as you saw on the previous page. And we use this final best split point to divide the node into left and right, like this. And we update the indexing list of the split data. It's about updating things like node set and row set that we looked at on the previous page. This is the horizontal partitioning method. Next, let's look at the vertical partitioning method. Cut the data vertically for each feature. The worker thread 1 creates the histograms for the first feature, and the worker thread 2 creates the histograms for the second feature. And find the local best split point for each feature. These correspond to the points A and B on the previous page. Choose A or B, whichever has the greater gain, as the global best split point. We then use this split point to divide the node like this. Now let's simply implement this algorithm. Let's do parallel processing using the multiprocessing library. The data we will use is like this. Let's find the global split point by processing each feature in parallel using two worker threads. First, define the function that finds the local split point for the given feature. F is the feature vector. The first feature and the second feature values. The S point is the list of split point candidates. Again, Q is the number of bins. Then candidates are read one by one from the S point list. J denotes the candidate. Use this candidate J to split the feature values into left and right. Assign the data points smaller than J to the left node, and the data points greater than J to the right node. And calculate the GL and HL using the data points in the left node. Then calculate the GR and HR of the right node using the G and H of the parent node and GL and HL of the left node. And we calculate the gain using this formula we looked at in XGBoost. The gamma is set to 0 here. Among all the candidates, find the one that has the greatest gain. This is the local best split point for the given feature, F. And it returns the local best split point and the max gain. Now let's use this function to find the global best split point for this dataset. Use 0.5 as the initial prediction. Calculate G and H for the root node. And create the histogram for the root node. The number of bins is set to 30. Create histograms for the feature 0 and the feature 1, respectively. The weights parameter is set to G. We then use this formula to calculate the score of the parent node. Now let's find the global best split point using parallel processing. The vertical partitioning method is used. Since there are two features, we use two worker threads. Set the argument to be passed to the first thread and the argument to be passed to the second thread as follows. We then have each worker thread execute the find local split point function defined on the left. The results are like this. The local best split point for feature 0 found by worker thread 1 is at this location. And the gain at that point is this value. Then we can get the following results. If the gain 1 is bigger than the gain 2, the first feature is the best for splitting. And the local split point of the feature 0 becomes the global best split point. If the gain 2 is larger, the second feature is the best. And the local split point of the feature 1 is the global best split point. This is the global best split point for entire data set. The results of the global best split point are as follows. The position 0.231 of the feature x0 is the best split point for the root node. Let's run this code. The results came out like this. So far, we've looked at the histogram-based algorithm. In the next video, we will look at the gradient-based one-side sampling, the GOSS algorithm.